Okay, welcome back to another video. In this video, we're actually going to cover some Stage 1 Specialist Mathematics questions from Chapter 7. All right, so I have a little list of questions I've been asked to do, and I'm going to go through them in detail, in sequence as well. So let's start off with rational numbers. So I've been asked to do question 4. So let's go to that one. All right, so question 4 is actually a bunch of parts. Now, there's different variations of how to do this, but in particular with the ones in terms of odd and even numbers. Now, the idea I like to think about a number which is, let's just say we've got A. A is in the set of integers. Okay. All right, so A is in Z. Then I could say 2A is even. Because that's, you can think of any number, probably if you don't include zero, there might be, I don't know, is zero an even number? Not really, it's not a, odd or even, but yeah, I'm gonna let that go for now. So 2A is even. Okay. So, but we need another one. Okay, so we're gonna have well, we've got A, and then we got B. 2A is even and 2B is even. Okay, so those are my even numbers. The sum of two even numbers is even. Well, so any number times by 2 is even. So you know 2, 4, 6, 8, 10, 12, so on and so forth. All right, well, this one's very easy. So prove the sum of two even numbers. So let's add them. If I go 2A plus 2B equals, now I can just write 2A plus B. All right, well, that is even. Because the A and B will just make another integer, and 2 times A and B is even. There you go. That's all there is to it. At least I'm satisfied with that as a proof. Um, okay, let's try another one. Sum of two odd numbers is even. Now, if 2A is even, then 2A plus 1 is odd. Or minus 1 if you prefer. Yeah, I'll just do plus 1. So 2B plus 1 is also odd. Okay. So in that case, let's add these. 2A plus 1 plus 2B plus 1. Whoops, I'm getting ahead of myself, but right, 2. Okay, then 2A plus B plus 2 equals 2. Yeah, actually, no, I proved it. A plus B, if I should have just factorized all of them. There you go. A plus B plus 1 is an integer, and any integer times by 2 is even. And I should probably write these statements. The proof should be for all A, B in integers. So you should actually finish up your proofs with statements like this. All right. All right, the difference of two rational numbers is rational. Okay, let's try this one. So we'll write two rational numbers. So I'll say for A, B, C, and D are included into a set of integers. Then A on B and C on D are rational. Oopsies, you can't see that. There you go, now you can. All right, so let's write the statement. So the difference of two rational numbers is rational. Let's just do A on B minus C on D. Okay, so let's see if we can write that as a single fraction. Using, all right, so I'm going to times D on D and B on B. So then I have AD minus BC on BD. All right, now this is rational because AD minus, whoopsies, AD minus BC is in the set of integers and BD, right? BD is also included in a set of integers because integer times integer is integer. I probably actually should have said for at the beginning, I should have said BD do not equal 0. That's important. But other than that, it's fine. For all A, B, C, D included in the set of integers where C, D do not equal, sorry, B and D do not equal 0. Okay. All right, and finally, the product of two rational numbers is rational. That one's actually probably the easiest one. Let's just go with the same numbers. A, so D, I'm just working with the same assumptions. A over B times C over D equals AC on BD. Now, because is rational as AC, BD are integers. So the denominator is an integer, the numerator is an integer, the numerator is an integer, so therefore it's rational for A, B, C, D, included in the set of integers where B, D are not equal to 0, comma, B and D are not equal to 0. All right, so that's the first one of those ones. Okay, so let's have a look. So next question I'm going to go through. 7c question 7, division by sets. Okay, this one, yeah, it's a bit messy. All right, find the positive solution for the equation of that. Okay. That seems like a bit of a mess. But hey, it's a quadratic, so it should actually conduct itself with the quadratic equation. Do I really want to do it that way, though? Let's just see what happens. Let's just do it and see what happens. The other way you can do it, there is a kind of another method. Completing the square, I think that's about as bad anyway. Because it's equal to 0, you can also multiply it by something just to make it a little bit nicer. You know what? I just feel like I'm just going to stick in the meat grinder and see what happens. So remember, the quadratic equation is minus b plus or minus b squared minus 4ac over 2a. This is going to get messy. All right. All right. So minus b minus 5 plus 2 root 5 plus or minus bracket. I'm going to need a big bracket. Blah, blah, blah. This squared. I'm feeling I'm going to get this wrong. All right. Yeah, I'm inclined. I've actually already said that I'm going to put a couple of these out just for the sake of expediency and the sake of me making mistakes, which happens on a frequent basis. I'll kind of set this up first. And then I'm going to show you the word solution version. All right, so on 2a. And we'll see if their method actually is the same as mine. If there's a much simpler method, then I've saved myself a bunch of time, then I've saved you a bunch of time. Okay, so I mean, that's one way you could do it. You can expand, you can simplify, you can mess around with the roots until things kind of nice out. Now, you also can just get rid of the plus and minus and just make it a plus because I said they want the positive solution. That's already larger than that, so this has to be positive for that to be a positive solution. So I said the positive solution, so find the positive solution. So yeah, that plus. But I'm gonna have a quick look and see how they do it on here. And you're welcome to pause the video when I show you this, and you can just have a look at their solution. But I'll just kind of talk through the major features. All right, so let's go to the word solution. Now, I've actually put this up on another section, but I will go back to that in a minute because I do want to show you those ones. All right, so 7c question 7. So they might have actually gone and approached it in a way it's a little bit simpler. All right. Hmm. So they've actually gone and what they actually worked out the discriminant first. So they've actually gone and reduced this, which is nice. So that's that section in the square root. So that's 225. All right. And then they've got the minus b plus or minus there, and they've reduced that. And they've gone, okay, so they reduce basically this is what would have happened. I'm just doing this inside my square root. So you work that down, you reduce it to this. Then you times by the conjugate. Actually, you reduce it to that, then you times by the conjugate to rationalize the denominator. Then you take the positive solution and you simplify it to a single statement. That's how you do it. All right, so I'm actually not going to continue with this one because I'm liable. I've got the method correct, but I'm liable to make a mistake, and you won't get the correct answer, and you just see the correct answer anyway. All right, so that's the method there. So I'll leave that one. Okay, so I'll come back to that in a minute. Let's have a look. What else do we have to do? All right, so yeah, these ones I'm going to use the word solutions for pretty much the same reason. 7D, 1C, and there's also 3B. All right, 3B and 7C. So let's just go to those ones. All right. All right. So proof by contradiction for the one here. So you start off with the idea. So you're trying to prove that this is irrational. So the cube root of 2. So if you prove it's irrational, it's a little bit different from the square ones. Okay, so so the cube root of 2 equals rational. So we're assuming that it is rational. I'm going to prove it's not. All right, so let's assume that root 3 of 2 is rational. All right, so written in the lowest term, p and q have no common factors. That's important when it comes to the disproof. All right, cubing both sides. 2 p cubed q cubed. Okay, and then you can write p cubed equals 2 cubed. So yeah, 2 cubed. All right, so p has a factor of 2, so then p cubed is a factor of 2, so p must have a factor of 2. All right. All right, because yeah, if you got something cubed, yeah, that's true in this case. So p cubed, if there's 2 of them, then this must also have the p has to also have a factor of 2. It's the only one that works. All right, so then you let p equal 2k, and then you find a statement here. So 8k cubed equals 2q cubed. All right, so then you can actually reduce that down. Q cubed equals 4k squared. So q cubed has a factor of 2, so 2 must have a factor. So q must have a factor of 2. However, we've already mentioned at the start, we wrote this as the rational in the lowest terms, so they had no common factors. So then this is a contradiction. They can't both. So the idea, the assumption that this is a rational written in the most lowest terms is being contradicted because they both have a factor of 2, so then they have no common. They must have common factors. All right. Here we have a contradiction as P and Q have no common factors, thus our original supposition is false, and the cube root of 2 is irrational. All right, so that's the proof of contradiction for 1C. Let's have a look at the other one we needed to look at was one of the logarithms, 3b. All right. So again, I believe this is proof by contradiction. Let x equals log 7 of 11 and suppose x is rational. Therefore, x equals p on q, where p and q are included in the set of integers, q is not equal to 0. And since x is greater than 0, integers p and q are greater than 0. Yeah, that's important because any output of a... Is that the case? Yeah, actually, yeah, any log that of any number greater than 1 will be positive, so that's true. Now, so x is the solution of okay, so the idea, if you undo the power, all right. Oh yeah, we did. So I'm doing the power of the logarithm base 7. So yeah, I did apply 7 the power of to both sides. Then you get 7 to the power of x, and you have log 7, 7 to the power of log 7, 11. Therefore, just 11. All right. Now x is the solution of that. 7 to pq. If you apply the power of q on both sides, you have 7p equals 11q. And this is impossible since 7 and 11 are prime numbers, as p and q are integers. Thus, the assumption is false and the opposite must be true. Um, so the idea, if you look at this, if you take the powers of 11, I think they all end in 1. Your powers of 7, well, basically, they're not common. So the idea that you're not going to find solutions of these. So this is not possible. Hence, x is irrational. All right, so yeah, I'm thinking that I will put a proof, but it's going to be a simpler one than some of these. Okay, so let's have a look at some of the other questions. All right, so I've also been asked to go through 7F, 3, 4, and 7. Let's look at that. 7F, 7F2 in particular, 3, 4, and 7. All right. All right, 7F2. Well, so let's get this a little more centered. There we go. Some more space. Mentor over a little bit. There we go. There we go. That'll do. Let's switch. Yep. All right. So 3, 4. What's the 3, 4, 7? 3, 4, and 7. Yes. 3. Okay. Start with question 3. All right. The complex number z satisfy the equation 3z plus 17I equals iz plus 1. All right. Write z in the form of a plus bi, where ab equals again. Yeah. All right. So all right. Well, let's actually express it that way. So I'm going to write it out. 3a plus bi bracket plus 17I equals I times a plus bi. That's my place, plus 11. Okay, so we got that so far. Now, next part, expand, simplify. 3a plus 17 plus b, lots of I. On the right-hand side, IA, actually I'm going to put that over here, A. Now, I times BI is minus B. So we have 11 minus B, that's the real part, plus AI. Okay, so now, you end up with two equations. The thing of equality of complex numbers, remember, the real part equals the real part. So 3a equals 11 minus b. Let's write that out. 3a equals 11 minus b. And the imaginary parts must equal. So thereby 17 plus b equals a. All right, well, let's just substitute the bottom one into the top. So then 3 lots of 17 plus b equals 11 minus b. So 17 times 3, that is 51 plus 3b equals 11 plus minus b, minus 40. Okay, b equals minus 10. All right, now question 4. So express z in the form of a plus bi, a and b including a set of integers. All right, and z is equal to, okay, we got this. Okay, let's just go, okay, that's a bit of a grind, but let's give it a try. All right, so let's work out 4, 1 plus I minus, no plus, 7 minus 2I. Um, hmm. Include 2 minus whether I should square that straight away or later. Let's wait for later. Okay, I'm actually going to take the conjugate and simplify this. All right, then I'm going to mess it up. Okay, so if I do that, then I'm introducing the conjugate there, and I'm going to express that. So that would actually be the sum of 2 squares. So actually 4 is 4 minus 4I on 2 plus 7 minus 2I squared. Okay, so simplified that. 4 divided by 2 is 2 plus 7 is 9. And then you have minus 2I minus 2I is minus 4I. Okay, that's a little bit nicer. Let's square that. All right, so 81 minus 2 times 4 times 9I. And then you would have minus 16, because that's minus 4I times minus 4I is negative 16. All right, so you got that. And then let's reduce that a little bit more. 81 minus 16, 71 minus 6 is 65. And then 18 is minus 36i. There's your answer. Okay, last one out of this set. Question 7. Over here. Question 7. So, a plus bi squared equals minus 16 minus 30i. Can you see that? Not quite. Let's bring it over. All right. So expand this out. Okay, left-hand side, a squared minus b squared. That's a squared, and the square of bi times bi is minus b squared. And there's there's the middle part, which is I've written this in terms of the real magic part because I've just that's the expansion anyway. So there's real and imaginary. Okay, so minus 16 minus 30i. Okay, so first equation, okay, you've got a squared minus b squared equals minus 16. All right. um, Yeah, it doesn't really jump out at me what to do next. The next part would be 2ab equals minus 30. I can simplify that at the very least, so that's minus 15. I can write something on the lines of a. Yeah, this is going to get a little bit tricky, but nothing. You have done this before. Okay. Um, so let's substitute this back into here. Minus 15 on b squared minus b squared minus 16 equals minus 16. All right, so what's that? 15 squared, 55. Where's my calculator? Yeah, I'm going to be doing this one with the test if I need to pull out a calculator for it. All right, 15 times 15, 225. All right, on b, okay, minus b squared equals minus 16. If it's times by b squared on both sides, what will happen then? Okay, so two. I had a feeling this might be quadratic, but I don't think it is actually. Yes, it will be, but it's a special type. It's actually kind of order 4, but it's still kind of a quadratic. I'm not sure if I've gone about this in a unnecessarily. Oh, that won't be 4. That'll be 2. Okay, I'll write this like this: 16b squared minus b power 4 plus 225. Okay, that's actually a quad. It's equal to 0. Sorry, I brought everything across one side. Okay, so this. Oh, actually, no, I've got it reversed. That's actually just times by minus 1. I'll turn it the other way around. All right, b to the power 4 minus 16 b squared plus minus 225. Okay, equals 0. Ho hum. Okay, now it is a quadratic, but the idea is I know it's got power 4 and power 2, but if you just think about it, if you replace b squared with something else, like if you let b squared equal x squared, or equal x, then this would be x squared minus 16x minus 225. If we just solve for that, and then, well, b has to be a real number, so we take solutions. Yeah, look, I'm just going to do this on my calculator. If it doesn't work, if this gets really ugly, then I'm just going to look at the word solutions again because I'm not going to waste too much time just doing one question. Okay, 1 minus 16 and minus 225. Okay. All right, so 25. So x equals, I'm taking x equal 25 only because I need to take the square root. Well, b can be plus or minus 5, in other words. So if b is plus or minus 5, that means b squared is 20. Yeah, b squared is 25. And if I put that back into these equations here, so if I take just a little space over here. All right, so if I go back to these equations, all right, we had a times b equals 15. All right, so if b equals minus 5, then a must equal 3. And if if b equals positive 5, then a must equal negative 3. Does that make sense? All right, to satisfy that anyway. Does that satisfy the other equation? Okay, a squared minus b squared. Well, a squared is always 9, and b squared is always 25. So then I think that works. And then so a squared minus b squared equals negative 16, like they want. So, yeah, that seems to work. So I believe there's actually 2 solutions. So z is that word x. Z is either 3 minus 5i or minus 3 plus 5i. Those aren't conjugates, but yeah, you get the idea. Okay, that's that lot of questions. Let's have a look at some other ones. Okay, so the last ones were 7G2. All right, questions 4, 7B, and 8. All right, start with question 4. All right, let's go have a look. Complex conjugates. Okay. Question 4. All right, an easy way of proving that is to start with, okay, so I think I tried to prove one of these and I realized if I prove the multiplication one, then I can prove that one easier because the way to prove the division one's really hard without the first one because it gets really long and messy. I realized I was doing that in class and I said, nah, I'm not doing that anymore. Let's just change it up. Let's see how this works. Okay, so if Z1 Okay, so let's start with the left-hand side. All right, so we've got the conjugate. Now what you can do with that, it's a neat little trick. You can bring that inside because we've already proved the multiplication. If you start with the assumption that you've already proved the multiplication, so we basically, if we start with the assumption that we've already proved, yeah, we've already proved that. So 16b. Then, okay, so that's Z2 actually. All right, then that's actually equal to Zi. No, Zi conjugate to be precise. So, but if I was then to multiply top and bottom by, so because I've cancelled those, because I can bring this inside because they both have the conjugate. Bring that inside. They cancel on the inside. I'm left with this, but then I can also just go, well, why can't I just reintroduce them again like this? So Z2 on Z2, and I put conjugate on conjugate, and then I can just write it like this: Z1 conjugate on Z2 conjugate times Z2. So what I've done there is I've actually proven, so then, yeah, well, I'll do it this way. Okay, then if I write this out again, so this is where I started. This is my first statement. Now these are all equals. I haven't done anything else. Times Z2 conjugate equals Z1 conjugate, Z2 conjugate times Z2 conjugate. Divide those off, and I've just proven it. So conjugate of bracket Z1, Z2 equals Z1 conjugate divided by Z2 conjugate. So that's how you do that one. There's a very quicker way of proving the division one. So I like it. All right, 7b, turn the page. That's what I thought. Okay, I have to prove 7a first. So let's do that. 7a, because I don't actually know what it is off the top of my head. No, actually, well, I've kind of done it already. Z squared equals, okay, a plus bi squared. Now, by the perfect square rule, you end up with a squared minus b squared plus 2abi. Now, I write it that way because I've done it that many times. A squared, bi times bi is minus b squared, which is real. And then you've got the 2 times a times bi equals 2abi. So there's the real and imaginary part. Okay. So we've got that in that form that they want. So x plus iy. Hence show that, okay, so z squared conjugate would equal a squared minus b squared minus 2abi. So that's the left-hand side. Right-hand side. Z conjugate squared. Well, that's a minus bi squared. Okay, the expansion of that is a squared minus b squared again, because it's minus bi times minus bi is, there's three negatives. There's the minus, and the two coefficients. There's the I squared. So that's how you still end up with this. But you end up with minus 2abi in the full expansion. Try it for yourself. You can do it by FOIL. You end up with this when you reduce it down, which is equal to the left-hand side. And thereby we proved it. Last one. Oh no, actually that was part B, wasn't it? Yep, so there we go, not part B. Okay. Question 8. All right. So what we're going to do here. Okay. So W. Excuse me. Okay. Z minus 1 and Z conjugate plus 1. Okay. Right. All right. So I'm not sure if you entirely need to do this, but I think I've done it this way before. This is a question I remember seeing in like the specialist books. So do A minus 1. I'm actually going to write the Z as A minus BI, but I'm also going to kind of just go straight for the real and imaginary part. So the real part of Z is A, and we also have minus 1, so I've written it that way. All right, and the conjugate here, I've got, I have A plus 1, and I have a minus BI, I should say, because that's the conjugate of Z. All right, so I'm actually going to times top and bottom with A plus 1 plus BI and A plus 1. I'm not sure why I put the second bracket there. I just put the brackets just to denote the real parts, like the all part of the reals. But the expansion of this, we have A minus 1, A plus 1. We have, we also have another real part, which would be BI times BI would be minus B squared. We have imaginary parts when we multiply that and that. We have plus A plus 1 B and B and A minus 1 B also I, and we have A plus 1 squared plus B squared. Okay, sorry, you can't see that. All right. Not sure what else to do with that in this stage. Maybe I'll just write out. I'll write out one more line. I'll make it a little bit neat. Trip my page. Okay, I'm just going to tidy it up. So the first part I can write. Okay, A minus 1 and A plus 1. It's the difference of two squares. A squared minus 1 minus B squared. That's the real part on the numerator. And I have okay. The imaginary parts I can write as I have plus A plus 1 times B and A minus 1 A minus 1 times B. All right, so the B's actually cancel in that case. So I have 2AB, and I have B and minus B. So that's actually it. That's the numerator, and the denominator is A plus 1 squared plus B. Okay, now I can actually write that as real and imaginary parts, A squared minus 1 minus B squared over denominator. And the imaginary part, same sort of thing. A plus B squared plus B squared. Sorry, A plus 1. Okay, there we go. All right, now that was a lot of work, but now it's going to pay off. Okay, what happens when W is real. What that means is 2AB equals 0. So that actually tells you one of two things. Either A equals 0 or B equals 0. Or both, but which basically means that W equals 0, which is kind of trivial. Okay, now if A equals 0, so let's just go with this one. If A equals 0, then you've got this still got this real part, which is kind of that. But what it becomes then is minus 1 minus b squared on 1 plus b squared, which is, I took the minus out of that, minus 1 plus b squared, or 1 plus b squared is minus 1. Okay, let's take the other scenario. B equals 0. A squared minus 1, and you have a plus 1 squared, which you can actually reduce, because this is the difference of two squares. That's how we factorize in the first place. Okay, I can cancel that with that, and I have a minus 1 over a plus 1. Not sure if there's much else you can do with that. Yeah, there's a bunch of solutions. No, by the looks of it, I don't see why that wouldn't be. Oh, my A's. Well, my A's a lot like 9s. I know people pull me up for that. So, yeah, I think that's kind of it. Let's have a look at B. So what if it's imaginary? That means this. Now, that means, you notice I just took the numerator, though, when I did this, because you can't divide and get 0. So when you get a fraction equal to 0, then you might as well just do that. A minus 1 minus B squared equals 0. Excuse me. This seems to be a relationship. All right. In any case, basically, you end up with All right, let's just see what that does. Let's just have a look at 2ABI, if that's the case. All right. So if I go in to replace that, I might even just look at what the word solutions. Check if I haven't made a mistake. Let's just do that. Word solutions. Let's just double check that. I haven't done anything wrong. I'm thinking of it. I'll substitute that into there and just kind of work out what it kind of, if it reduces to anything. Let's have a look. To question 8. Yeah, it's a bit of a mess. And yeah, it is pretty much that. Purely imaginary, yeah, that can't be equal to 0. So A must be equal to 1, B and 0. But that's it, really. Okay, you can't, well, that's kind of it. So yeah, what I wrote is kind of that's it. So that's it. You just have a relationship between A and B that reduces kind of like, if you know what A is, you can work out B. Or at least one, a couple of solutions of it. All right, so that's all the questions. So I will catch you in the next video. Bye-bye.